Imagine you have two separate regions in the plane. Any shapes you want, irregular, curved, completely arbitrary, they don't overlap. Now here's the challenge. Can you find a single straight line that passes through both regions and divides each one into two pieces of exactly equal area? It sounds impossible, but I'm going to prove to you that it's always possible. Let's be precise. Region A has some total area, call it capital A. Region B has total area, capital B. We're looking for a single line that splits region A into two halves of area A over 2 each, and at the same time splits region B into two halves of area B over 2 each. This line must pass through both regions. We're asking, does such a line always exist? Here's the first key insight. Imagine a line sweeping across both regions from left to right. Fix the direction, say horizontal. As the line moves, the amount of area to the left of the line increases smoothly. For region A, it starts at 0 and increases all the way to A. For region B, it starts at 0 and increases all the way to B. Both are continuous functions of the line's position. By the intermediate value theorem, as the area of region A on the left goes continuously from 0 to A, it must pass through A over 2 at some position. There is always a horizontal line that bisects region A. Call this the area bisector for region A at this direction. The same argument applies to region B. There is always a position where a horizontal line bisects B. But here's the catch. The bisecting line for region A and the bisecting line for region B are at different positions. There is no horizontal line that bisects both regions simultaneously. So the question becomes, can we rotate the line's direction until we find a magic angle where the two bisectors coincide? Imagine rotating our line's direction continuously, starting from 0 degrees and rotating all the way around to 180 degrees. As we rotate, the position of region A's bisector changes smoothly, and the position of region B's bisector changes smoothly. These positions trace out paths as a function of the direction angle. The magic happens because when you rotate 180 degrees, left and right swap, so the bisector positions flip. Let's think of this more formally. For each direction angle theta, there is a unique position dA, where a line bisects region A, and a unique position dB, where a line bisects region B. These give us two functions, dA of theta and dB of theta, both varying continuously. We want to find an angle where dA equals dB. Here's why it must exist. When we rotate the direction by 180 degrees, the roles of left and right reverse completely, so dA at 0 degrees and dA at 180 degrees have opposite signs. The same is true for dB. This guarantees a crossing point. Consider the difference function dA of theta minus dB of theta. At one angle, this difference is positive. The A bisector is further right than the B bisector. At another angle after rotation, this difference is negative. The roles have flipped. Since this difference function is continuous in theta, the intermediate value theorem guarantees that at some angle in between, the difference is exactly 0. At that angle, dA equals dB. The A bisector and B bisector are at the same position. That line divides both regions perfectly. There it is. One line passing through both regions, dividing each one into two pieces of equal area. It seemed impossible, but topology and continuity forced it to exist. No matter what shapes you draw, no matter how irregular or chaotic, this magic line is always there, guaranteed by the continuous nature of area and rotation. This is a beautiful example of an existence proof. We never explicitly constructed the line. We just showed that the forces of continuity and symmetry under rotation make it inevitable. And here's the kicker. This doesn't just work for two regions. The same argument extends to any finite number of non-overlapping regions. For n regions, you can almost always find a line bisecting all of them simultaneously. It's a reminder that sometimes the most powerful tools in mathematics aren't formulas or calculations, but pure, elegant